As I said yesterday, this isn't normally how I would do it. Normally we would finish the lab today, although you guys got quite far yesterday. I was quite happy, although I don't think a lot of people got to sort of the graphing and that kind of write-up part, right? Yeah, so it's usually a 2-day kind of event, and I wouldn't normally do it in this order, but unfortunately I'm not going to be here tomorrow morning. So we'll do it this way, and you sort of get a bit of a foreshadowing, well, more than foreshadowing, you'll be told exactly what your results are going to look like tomorrow kind of thing. So we can jump right in. I would suggest you write down some stuff. Be warned, there's some heavy algebra in your near future. Okay? Please do not write everything down. Let's begin. So, I think those new apparatuses worked pretty well. I was pretty pleased with the results. Although I think, would you all agree that the strings were a bit long?
Yeah.
Yeah, so maybe I need to cut the strings back a bit. Okay, so I'll put that on my to-do list. It'll be in spot number 99. Okay, so we're going to take the results of our experiment and derive some formulas, and everyone loves to derive formulas, right? That relate. Is that a yes? I love to derive formulas, or is that I have a question? Oh.
When we do like the last where you'll derive the formulas with us and then we can just keep it.
Absolutely, yeah. Yeah. No, you do not have to, I will not expect you to derive these. I can't do these without notes in front of me. And I've done them several years in a row. Yeah. This is more just an experience. Okay, so we're going to derive formulas that relate centripetal force Fc to various aspects of UCM. And that was actually, if you look at the purpose of the lab, it basically says that, right? There's three variables. What were the three variables in the lab? The first one that you did was the number of washers, which is the centripetal force. The second thing you did was the radius, right? And then the third thing, if you got to it, was the mass at the end, right? So those three things all affect the period. So to begin with, when you did period squared versus centripetal force, did anyone get the graphs done? Does your graph kind of look like that? Was it an inverse relationship? Yeah. Okay. So this suggests that it may be an inverse or possibly inverse squared relationship. Okay. Back in the good old days before computers and trend lines and all that kind of stuff, they would actually take that and they would actually have to do what you guys did, which was to confirm what kind of it was, is they would graph t squared versus, it's way in the corner here, t squared versus 1 over fc. That's 1 over fc. Okay? And if you get a straight line when you graph t squared versus 1 over fc, then you know that 1 over fc is the linear one, and then in the original one was actually an inverse. If you don't get a straight line, if you get a curved line, then it must be t squared versus 1 over fc squared, and then you would get the straight line. Okay, so that's how they used to do it back sort of in the old graph paper days. When you graphed it, did you get to the second one? Did it turn out to be reasonably straight? Okay, and I saw a couple, and was it yours, I think, Peyton, your group there, that you thought that it was kind of lousy, but then once you draw the trend line in there, it actually doesn't look too bad, right? So this suggests that the period squared is proportional to 1 over fc. This funny looking symbol right there means proportional to, which means that as the centripetal force goes up, as you get more washers, right? As you get more washers, if you've got 1 over 10, 1 over 20, 1 over 30, the fraction gets smaller, which means the period gets smaller, right? Did you find that? As you put more and more washers on, it went faster? Did you find that? And it's actually a t squared relationship, right? Sort of removed one aspect of that for you. Okay, so we've got t squared is proportional 1 over fc. That is what you discovered, whether you knew it or not. That's what you discovered, whether it was qualitatively, yeah, it got faster as we added more washers, or numerically like this, right? That's what you discovered from part A from yesterday. When you get to part B and you change the radius, qualitatively, what did you find as you changed the radius? Did it get faster or did it get smaller? Or faster or slower? As the radius went out, what happened to it got slower, which would increase or decrease the period? Increase, right? Slower means takes longer period of time, period. So you should have got a graph like that. You should have got a linear graph, which implies that t squared is proportional to r. So the second relationship that you discovered yesterday, whether it be qualitatively or quantitatively, is that the bigger the radius, the slower the thing object rotates, right? The slower, the bigger the radius, the greater the time. Bigger radius means bigger time of revolution, which really means slower speed, right? And I think if I asked you to begin with, before doing anything, you probably would have been able to figure that out. Or you're just in your intuition would have said, yeah, if I've got a big long string, and it's got to go all the way around, it's going to be slower, it's going to be a greater period, right? I think that just sort of makes sense. What should you write down out of this? You should write down t squared is proportional to r. Okay, now only a couple groups got to the rubber stoppers, right? The adding of the extra one. Those of you that did it, Chris, your group did it, and was there one other group too? Oh, Anderson? Okay, so Anderson, what did you guys discover? As you added stoppers, did it slow down? Or did it speed up? It sped up? Chris, would you agree? Can't remember? Can't remember? Okay, well, what you should have got was a linear one, again. So this is t squared, and this is mass. So Anderson, I hate to tell you this, but as the mass goes up, the period goes up, which means it goes slower. Which sort of makes sense, because there's more mass, right? Greater force required, force is the same, so the acceleration should be less. So it should actually go slower. So this implies that t squared is proportional to m as well. So out of all that, we got 3 proportionality statements. Wonderful. What good are they? Can you do anything with them? You can combine them into a formula. Only someone in the room knew how to do that. By combining these 3 proportionalities together, you're going to get t squared is proportional to rm over fc. And I'll just pause there and sort of let you get this down. And then we'll discuss it. Okay, so by combining the proportionalities together, you get t squared is proportional to rm over fc. All I did was take t squared is proportional to r, t squared is proportional to m, and t squared is proportional to 1 over fc and combine it together. Now, when you take a proportionality statement and you create an equation, you need a constant of proportionality, some number that makes it work. Let me demonstrate, or let me explain with a formula that you're probably more familiar with. Area of a circle is proportional to the radius squared, right? As the radius of the circle gets bigger, so does the area, right? But it's not an equation. That's a proportionality statement that no one ever uses, right? You all know area equals pi r squared, right? What is pi? It's the constant of proportionality. It's the number that turns it into an equation. No, but pi in this instance is the constant that makes the equation work. Okay? Pi also appears in, pi is a common one, right? C equals pi times diameter, right? That's another common one. Think chemistry. It's been so long since I taught chemistry. A mole, that's a constant of proportionality. In Einstein's famous equation, E equals mc squared, the constant of proportionality is actually the c, speed of light squared. Planck's constant. Anything that has the word constant in it is a constant of proportionality. Okay? So, K is the proportionality constant. And all I did here was I rearranged FC, I switched FC and t squared so that my formula is arranged like this, because people are more concerned about the force than the t. I don't know why. They want the F over there. Okay? So now our job is to come up with what is our value of K? What is our value of K? Do you have a feeling that pi might be involved? Brandy did ask it. Is it pi? It's not pi. But is pi involved, do you think? You think so because we're talking circles. Okay, so we're making a prediction here, and then we're going to show the algebra to do it here. So with FC equals KRM over T squared, let's compare this to FC is equal to MAC. F equals MA, and all I've done is put subscripts on the F and the A because the F is what kind of force? Centripetal, which results in a centripetal acceleration, right? So I'm just comparing this to this, right? Look at the M, look at the M. So what do you predict the formula for AC is? Centripetal acceleration. See the M's? So what do you predict the A is going to be? Don't all shout out at once. Would you say it's KR over T squared? Right? This here, circled in red, is the A, right? So the predicted formula for centripetal acceleration is kr squared over t squared. So we're going to attempt to derive a formula, see if it matches our prediction, and see if it somehow leads us to this magical, mystical value of k. What is K? K stands for the proportionality constant, R is the radius. You missed a little bit, sorry. Okay, here's where the heavy algebra starts. Do you want to write and then let me talk? I heard a yes. And of course I have the recording paused that entire time. Okay, so centripetal acceleration, we've got A equals delta V over delta T, and we're going to rearrange that to delta V equals A delta T. And then we're going to replace just the generic delta T with a capital T for period. And then I'm going to say delta V T is equal to A times T. Okay, so the change in velocity, and the T just stands for the period. The change in velocity in one period is equal to the acceleration multiplied by the period itself. And we're going to call that saved equation number 2, again, because we're going to come back to it. Okay, I'm just sort of setting up for the finale here. Everyone good? I haven't done anything too sort of smoke and mirrors yet. If only there was a punchline at the end. Trust me, it won't be that much fun. Okay. Here's the slide that I hate. Put your pens down and just watch. Another way to think about delta V for a whole revolution. Suppose several instantaneous velocities are recorded. This is shown as these tangent lines below, okay? So V1, V2, V3, V4, and so on, right? You would have several tangent lines all the way around. They would all be the same length, or would they not? The length, of course, indicates the speed. So would they be the same length all the way around? They would, because it's traveling at a uniform, constant speed, right? The only thing that changes is the direction. So they would all be the same length. In fact, it even says that right there. Each vector V1, V2, V3 is the same length as the speed is constant. The value delta V is the difference between them, which is in red here. By the way, I do not relish this explanation. If you were to place V1, V2, V3 all the way to V8 tail to tail, would it look like this spoked wheel kind of thing? Right? Like if you took this V1 here and that V2 and that V3, right, and you sort of pulled them off. Whoopsie, I want that. It doesn't take too much imagination. It doesn't take too much imagination to see that they would, and they're obviously not the same length, they should be, right? It doesn't take too much imagination to see that you would actually get this kind of thing, would you not? Okay, let me put those back. And in this fashion then, delta V1, delta V2 would be something like this. This would be delta V1, delta V2, delta V3, delta V4. Don't write this down, by the way. Just enjoy it. Thanks for that snicker, Joe. Okay? So the total change in velocity, delta V, big T, is delta V1 plus delta V2 plus, and so on. And if you imagine that I didn't have only 8 instantaneous velocities, but rather 100, 1,000, 1,000,000, what would 1,000 of these things look like? Well, it would be completely black, and it would be almost a circle. This is an 8-sided figure because there's 8 arrows, but if I had 100, then the red figure on the outside would be a 100-sided figure, and if I had 1,000 black arrows, then my red circle would be 1,000-sided, and so on. And if it's an infinite one, well, then my red arrows are, in essence, a circle. Okay, it's kind of like a limit in calculus. You guys done that yet? Gotten there? Okay. Okay, it's kind of that idea of infinite and limit, and eventually becoming a straight line becoming a circle. Yeah. Okay, so in other words here, delta V1 plus delta V2 plus delta V3, or in other words, the circumference of the circle, 2 pi r. But what is the radius of said circle right here? V1, V2, V3, V4. The speed, which is constant, where radius is equal to V1, is equal to V2, is equal to V3, and so on. So instead of 2 pi r, I replace the r with V. Total change in velocity is 2 pi V. Saved equation number 3. Please do not spend hours worrying about this slide tonight. Just bask in its brilliance. Here's the big finale. Remember equations 2 and 3. They weren't that long ago. There was equation 3 right there. Right? Equations 2 and 3 were delta Vt is equal to At. And equation 3 was delta Vt is equal to 2 pi V. Let me put up the shade there. Okay? So I'm just rewriting them. Side by side, that's all I'm doing there. You will notice that both of them begin with delta Vt, which means what? We can put them together, right? At is equal to 2 pi V. Or, and we're getting close, or I can rearrange that for 2 pi V over T. We're going to call this saved equation number 4. We're very close. Now, look back. Equation 1 was 2 pi r over V. Do you see what's coming? Do you see it? Yes, we're going to. What are you going to get? You're going to get one of those dreaded double fractions, aren't you? Do you sense some canceling, though? I mean, look at, you got a 2 pi going in the bottom there, you got a 2 pi in the top. It's going to look messy to begin with, but do you get a feeling that there's going to be some canceling and it's all going to work out beautiful in the end? Just like a Hollywood movie? Oh, sure. This is equation number 1. We're going to take this value of t here, we're going to plug it in there. Okay, and I've just re-shown that on this next slide so you can see it. You don't have to redraw it, right? This is exactly what was just before. So this box 2 pi r over v is going to go in for t. And here's the big one. So you get 2 pi v over 2 pi r over v, cancel, cancel, v over r over v is AC is equal to v squared over r. All that work for that little thing. Centripetal acceleration is equal to v squared over r. Now there's an alternate one that comes out of this as well. If you choose to write this one here, 2 pi, instead of 2 pi v over t, can you write it as 2 pi over t and then times v? Is that the same thing? Order of operations? Remember spending all that time on order of operations? That was just so you could do this right now. Right? You pull the v off, so it's 2 pi over t times v. What is v equal to? Can't remember what equation it is, but it's equal to 2 pi r over t. You plug it in there like that. Is there going to be any canceling here? Not really, but there's going to be some combining. What's it going to be? Two times 2 is 4. Pi times pi is pi squared. R over t times t is t squared. 4 pi squared r over t squared. These are equivalent. When do you use this one? When do you use this one? Well, you use this one when you got the velocity. You use this one when you don't, when you know the radius and the period squared, or the period, I guess. Okay? All of this is included, right? V is the velocity in meters per second. R is the radius of the circle, must be in meters. A is the centripetal acceleration in meters per second squared, and T is the period. I'll pause. That's okay. I'll still sleep today. Okay, so we've got two formulas now for centripetal acceleration. Now remember, way back, what we really wanted to know was what our value of K was. I'll give you a hint. You already know. I just told it to you. I just didn't say, hey, there's our value of K. What was our predicted formula based on the experiment? It was KR over T squared. That's what you guys predicted based on your experiment, with a little help from me. What did we just derive? 4 pi squared R over T squared. Looking at those two things, what is your value of K? Right? R over T squared. R over T squared. What's left? K. K. So as Brandy, her gut told her that there was going to be some pi involved eventually. It's kind of like Thanksgiving dinner, you know, there's going to be pi. Four pi squared. Now, we also really wanted to know what the formula for centripetal force would be. Is this going to be another 6 or 7 slides? Why not? It's not going to be because I don't have enough paper for that. That's the reason. No, because I've given you the acceleration formula, and to get to force, all you have to do is, given our formulas for A equals V squared over R, or AC is equal to 4 pi squared R over T squared. If you want a formula for centripetal force, since F equals MA and FC is equal to MAC, and I made this way more complicated than I need to, all you need to do is put an M in front, multiplied by the mass, right? That's what you need to know, right? All you need to do is multiply by mass. This one here is the big one. That's the one that you'll remember at your 10-year reunion talking physics. mv squared over r. Yeah, right, whatever. Centripetal force is mass times velocity squared over r.
So, when we're using formulas, we believe obviously the force ones, but we would also be using the acceleration.
Yeah, it depends on what the question is asking. Yeah. I mean, really, all I've really given you is, right? Back in grade 11, you had F net is equal to MA, and you had A is equal to delta V over delta T, right? And you solved a bunch of problems with them. All I've really done is given you two new versions of A for circles. That's all I've really given you, right? When you boil it down right to the bare minimum, that's what I've given you. And then you can take that A, multiply by M to get the force. And that force is a centripetal force. That's what it all boils down to, right? Do you feel smart? No? Think back to grade 11 when you had to do like slope of a line. You're like, oh my God, it's just so hard. Remember that? It wasn't hard, was it? Stupid and annoying is what it was? Okay. I still get kids saying it's hard. This is as hard as it's going to get. Really. In sort of that sort of abstract kind of thought process. Always got to have a punchline at the end, right? Actually, a student said that to me. Mr. Bennett, I feel like I've been going in circles. So I had to put it in. I had a sweater like that once. It was the 80s. I did, and I had a computer like that too. I had hair like that. That's not me.